Hello, Mr. Malo here, your online math teacher, and welcome to my channel. Today we're going to be continuing my series on exponential and logarithmic functions. And if you find this video helpful, please consider smashing the like button, subscribing, and checking out my other videos. So we talked about what exponential functions were in my last video of this series. So now we're going to talk about what the natural exponential function is. And it's really a nice, in particular, value of a base we can give. So, and it really deals with the power of e, because e is a very powerful number in math. So, the number e rounded to 5 decimals is 2.71828. And usually I only make students know the first decimal, 2.7. I'm not one of these people that memorizes 10,000 decimals. And using this number e, we say the natural exponential function is the exponential function defined by e to the x with base e, obviously. And a lot of times we don't call it the natural exponential function because that's a lot to say at once. So we usually just say it is the exponential function because it is the most powerful one. And why is it powerful? Really ties into calculus. So when you take calculus after you're done with pre-calc, you're going to see that of all these exponential functions, e to the x has some really nice properties. That'll be the first place you'll see why this function is so nice. Now, just to comment on the number e, I rounded to 5 decimals here, but it has infinitely many decimals. It doesn't repeat, doesn't terminate. It's a transcendental number, kind of like pi. But usually you don't need to know too many values of it. I'm not one of these people that knows more than a few digits of pi, even though I teach math and have many degrees in it. But so I say 2.7 approximately. That's usually good enough to know. So its base graph, when we're not transforming it, looks just like all our other exponential functions. When I'm not moving it around and I want to graph y is equal to e to the x, the point 0, 1 is a point on every single one of our exponential functions. And then I know the point 1e is in it. So 1e right here. So I know it looks just like my other exponential functions. And the real reason, like I said, we care about this is because of properties it's going to have when you get into calculus. So we got the point 1e on our graph and 0, 1. Now, this is why I say you only need to know that e is of roughly 2.7. You're not going to be exact when you're plotting that point. And I'd buy that. I plotted that point right around 2.7 as far as its y coordinate. So 1e is roughly at 1, 2.7. So the first thing you're going to want to probably do in your classes is you're going to graph these functions, because understanding its graph is good before you start messing with it algebraically. So what you can do is graph your transformations of the functions. And just like in my other videos, I recommend knowing the base function, which you drew up there well, and then making a list of the transformations you need to apply. So why don't you try pausing my video here and making a list? Okay, hopefully you did, and you probably got the following lists. And I made these nice and easy ones, so there's not a bunch of transformations in them. But this first one here, all it has is a vertical shift translation up by 2 units, so you're shifting everything up 2 units. Always move your asymptotes first. Same goes for all these exponential functions. So if I move my horizontal asymptote up 2 units, that's now y is equal to 2. And I can apply the same thing to my points. My point is 0, 1, up 1, 2 units. My point at 1e is now going to 1e plus 2. And that tells you that your picture is roughly this. Similar thing over on the right here. This one again just has one translation to the right by 2 units. So this one actually doesn't move your asymptote. It stays there. But then each of these points gets moved to the right by 2 units. So you end up with a similar picture still. So transformations of functions aren't going to be any different with the natural exponential function than they were when you were working with any other exponential function. One thing that is a little different is that word problem we talked about last time. Compound interest problems are useful, and in particular, another way to look at it is compounding continuously. So we talked about last time how many times within your unit of time are you compounding? Annually once, semi-annually twice, quarterly 4 times, and so on. Continuously, you can kind of think of as almost infinitely often you're compounding it. So a lot of our values are the same here that they were before. So A of t is the value after t years, or it could be a similar time unit depending on your scenario. P is that principal investment, so the initial amount invested at time is equal to 0. R is still the interest rate, and we still need to make sure we're plugging it into the formula as a decimal. And T is typically number of years or a similar time unit. And the way I remember this formula is when I read it as PERT. And PERT rolls off the tongue pretty easily. I also remember seeing a shampoo brand called that once, so it's just another weird connection I have in my mind. So what types of problems can we answer with this? Stuff like exercise 2 here. If you want to find the amount after 7 years that's in account, if $10,000 is invested into it, at an interest rate of 12.75% and per year, compounded continuously. And if you find this account, send me an email. I will invest all my money in this because this is better returns than I can get in the stock market. So I'm just going to first write what is my compound interest formula. So I'm using PERT. And in this case, A of t is going to be equal to the principal amount invested. So 10,000 is how much we're investing at time 0. E to the r, so 12.75% is 0.1275 t. This is our formula. So if you want to know how much is in the account after 7 years, we're just replacing t with 7, because that means 7 years of time will have passed. So if we do that, you are going to get that this is approximately $24,412.25. Pretty good growth amount from that $10,000 you started with just for 7 years. So I hope this video helps. And if you liked it, hit the like button, check out my other videos, and have an awesome day.